What's up? Welcome back. In this episode, you'll learn how to solve day 16 for the advent of code in 2023. First, take a look at this. This is such a cool animation on the main page here. You can see the fire is just like falling down. Maybe that's our lava. Let's jump into day 16, which is called The Floor Will Be Lava. The floor is lava. Watch out. Okay. So right now we have worked on getting this beam of light focused. We went through and we changed a bunch of lenses in a box, and now it's pouring into this space. And we have a map of how the light is going to filter through and bounce against mirrors and splitters. We're taking a look at the contraption, and that is our puzzle input, is the layout of the contraption. We have several instructions about how the light beam will pass through the contraption. If the beam encounters an empty space, it's going to keep traveling in the same direction it's already traveling. If it encounters a mirror, one of the slashes, it's going to change direction. It'll be reflected at 90 degrees. If we're coming in from here, we're headed towards the east, and we bounce off of this mirror, we're going to go down, right? So we're coming in this way, we're going to bounce off there and come down. If we're coming at the mirror from this other side over here, we're going to bounce and go up, right? If we encounter the pointy end of a splitter, so a splitter is a pipe or a dash. If we encounter the pointy end, so if we look at maybe this pipe operator here, if we encounter the pointy end, like maybe we're coming down and we hit the top of it, we just keep going. Or if we're coming up and we hit the bottom of it, we just keep going. Same with the horizontal splitter. If we're coming from the left or the right, we just keep going. But otherwise, if we hit the flat side of the splitter, so if we're looking at this pipe again, and if we're coming from this side, then two beams of light are going to come out, one through the top and one through the bottom. As the beams travel through the contraption, they're going to kind of like leave a path of which tiles were energized. And so this gives us kind of an example based on that input of the direction that the beam is traveling. So first it goes here and then it hits this splitter. So it's going to go up, but that's off the grid. And it's also going to go down, 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 down. It hits this splitter. So it'll go to the left and the right. When it enters this splitter, it does nothing because it went in the pointy end of the splitter. And then it's going to hit this mirror and go up. And then it's going to hit this mirror and go to the right. And then it will hit this mirror and go down and split. And then it's going to go to the left and down and off the board. Our goal is to basically just follow the instructions here. We're going to have a beam that starts on this top left corner, is pointing to the right, and is traveling through this contraption. Because a beam can be split into two, we'll need to go through the contraption with lots of different paths. So I want to keep an array of the fronts of the beams. And if we encounter a splitter, we'll just add a new head onto the beam, and then we'll go in like the two directions away from the beam. The beam of light needs to know its XY coordinate and what direction is it traveling. And it's possible that a single tile can have beams that are traveling two different directions on top of it. For instance, this specific tile right here has a beam that is traveling to the right, and also a beam that's traveling down that can cross at the same time. That's totally fine. So we need to keep track of where we are and what direction we're headed. Ultimately, we count up all the tiles where the beam passed through. So if we grab this puzzle input, usually we drop it in just like this, right? We'll say input is equal to this thing, and then input. But if we print out input dot split on new lines dot map chars, you'll see something interesting. It's actually a little hard to tell based on this look here. So if we go through, let's just call this grid, and we'll say grid.each do row puts row.join. Okay. If you look at the grid and the way that it printed out, it does not look like a square, right? The input looked squarey, and Vim is telling us that something about these slashes is different, right? And so if you look at the output, we actually don't even see many of those backslashes. We only see one of them right here. And that's because Ruby uses backslashes to escape characters. So inside of this string, these backslashes are escaping the period in a way. So if we open up IRB here and just explore backslashes for a second. So if we have a string and we try to say, let's create a string with the backslash, then this doesn't actually give us anything. A is invalid, right? It's because we're still in the middle of a quote. We're like in the middle of defining a quote. So if we try this again, A is equal to backslash, and then we close the backslash, we end up with like backslash and then a new line. And the quote here is escaped. So the whole point of this is so that we can do stuff like this. We can say A is, they said, hey there, right? So that you can print out like the quotes around it. Now, when we evaluate this previous line, it's showing the inspected version. But if we do puts or put s for A, now like the string that was printed out has quotes around hey there. So the backslash here is a special kind of character that's used for escaping other characters. And if for some reason we needed to include a backslash in our output, the way that we would do that is by putting 2 backslashes. And if we look at this string, it looks like there's 2 backslashes, but if we puts A, there's actually only 1 backslash. And in fact, if we look at like a.length, it's only 1 character, a.ord. The ASCII value for A is 92. So if we look at this ASCII table and we look at 92, we see the single backslash. When we're defining a here doc here, this is a string. It's a type of multi-line string in Ruby. And this is expecting that we go through and add a second backslash to all of these. However, we don't want to have to do that on our input, right? If we run this, okay, so now it looks like a grid, right? But our actual puzzle input is going to be massive. We don't want to manually go through and add backslashes. Rather than adding our input like this, we want to read it from a file. So let's just add a new file.read, and we'll say /example. And that's going to be our input. So we're going to open up example and we'll paste in this, all because we have some backslashes. So now we can do Ruby main.rb and we see the backslashes as expected. So now we have a grid that we can work with. Now that we have this grid of characters, we want to figure out how we can travel through the grid. So we need to start with a list of beams, and our list of beams is going to start at basically 0, 0. And it will have a direction of, it's going to be heading to, yeah, we'll just say to the right. Okay. And what we want to do is while the beams are like have something in it, we're going to work our way through the head of the beams until we fall off the edge of the grid. What we want to do is grab the first, so X and Y and direction is going to be beams.shift. And then we want to say, okay, so we also want like a DX and a DY. And that is going to be based on the direction that we're already going. So if we're going to the right, then that means we want to not change the row. We want to only change the column, and we want to increase the column by 1. If we're going to the left, we're going to do the same thing, but we want to decrease the column. If we're going up, we want to decrease the row. And if we're going down, we want to increase the row. So dx dy is going to be the mapping between the direction of our beam and this pair of directions. That's going to give us a new grid coordinate that is like the next step forward if we were to follow the grid in this direction. And that's going to be grid at x dx and grid at y dy. And now what we can do is use pattern matching based on what's at the front. So we want to say case for the front. It's going to be one of these characters, right? A dot, a slash, a pipe, or whatever. If the thing that's in front of us is if it's a dot, then we keep going. If it's a pipe, then we maybe split. If it's in a dash, we need to split. If it's in a slash, we need to turn. If it's in the backslash, we need to turn. And then we might have some other cases here. While we're going forward, if we encounter this dot, what does it mean to keep going forward? It means that we want to add into our list of beam heads, like this new beam here. So we have dx, dy, and the current direction. So we're going to keep going in the same direction. Now, if we encounter a beam, we might want to split, but we also might not want to split. So here we can build our pattern matching not only on the type of tile that's in front of us, but we can also build it on the direction that we're currently going. So if we're going forward and we encounter a dot, it doesn't matter what the direction is. We're just going to keep following the same direction. But if we encounter a pipe and we're either going to the right or we're going to the left, then we want to split. But if we're going up or down, we don't want to do anything. We want to just keep going. All right. What does it mean to split? Let's see. In this case, if we're going to split at this position, we want to add into the beam our current position, and we want to add up and down. So when we're splitting on the beam, we're going to go up and down. Okay, and then we're going to do the same thing here, but instead of going up and down, we're going to go left and right, because if we encounter the flat part of this, then we're going to go both left and right from that same position. Okay, so that gives us our splits and our turns. Oh, and we only want to do this if we're going up or down. If we're going left or right, we're just going to continue on. So we'll also need an else case here. If we're in any other case, we want to keep going, which means that we might be able to pull off this one and put this in like the default case, but we'll see in a second. Okay, so if we encounter this slash, we want to turn. And it depends on what direction we're coming from, which way we're actually going to turn. And so we need some mapping between the type of turn. So I guess in this case, it's going to be slash, and that's going to point at something. Okay, so if we're going to the right, we want to go up. And if we're going left, we want to go down. And if we're going up, we want to go right. And if we're going down, we want to go left. And we might as well do the other one also. So if we're going to the right, we'll go down, left, up, left, left, up. If we're going up, we go to the left. Yeah, that's right. And then if we're coming down, we go to the right. Okay, so now we're going to say beams. We only add in one single beam in this case. And instead of direction, it's going to be like turn of slash in that direction. Does that make sense? So we're indexing into turns at slash, and that matches what we just pattern matched on. And then we're going to map from that direction to the new direction. Okay. Same with this one. So we're going to go from turn to the other direction. Okay, otherwise, we just put this in. I don't know if this is actually going to work. Let's see here. While we're traveling through all these different beams, we're probably going to encounter something where we fall off the edge of the grid here. So we want to also add something that says if x plus dx is less than 0, so this is if we're off the grid, then break or next. And this beams.shift is going to pull the front element off of the beam. So this is going to modify the underlying array, and eventually we'll get to an empty beam. We can keep track of a list of energized tiles, meaning like we've traveled through that tile. And at the end, we'll print out p energized.length. Yeah, let's just see what that gives us. Okay, 0. That's because we're not. So energized plus equals beams. And because we're using a set, that should be okay. All right, so we got back 20. And that's interesting. So let's look at what those actually look like on the grid. So we'll do grid.each do row. And then let's actually do each with index to row, row.each with index to cell. And we want to say something like if energize includes x, y, then print the pound sign, otherwise print a dot. And then at the end, we'll print a new line. Okay, but we have a problem here because our energized, like when we add the beams, they also include the direction. So here we need to have the list of energized without the direction. And it's almost like it's listening to me. Okay. All right, so now if we run this, okay, it looks like it split here, it came down, it split, and then it traveled here, and then it went like right through this. So something is going on here. Why aren't we... Let's take a look again. Okay, so we're starting at 0, 0. We're going to the right. It splits and comes down. And then here it splits and then goes across. It goes up. And then it just goes like straight off the edge over here. So it's almost like it's not encountering this backslash and coming down. So we've got to figure out why it's not hitting this backslash. Oh, because if it's, yeah, this needs to have an underscore for it to match there. Okay, so now we are hanging when we run this. So it's stuck in a loop. So now we need some way to know to break out, because if the light is just bouncing around inside of a loop, then we'll never come out of that loop. This isn't going to really work because we don't include the direction in energized. So we need to have another set that has the tiles that we visited along with the direction. So we're going to have some list of scene tiles here, and we're going to say something like, if we've seen it, then we'll skip over it. But we want to do this a little bit carefully because we don't want to just eliminate all of them. So again, right now it's hanging, and what we want to do at the bottom here is maybe we keep track of a subset of beams. So we'll call it like new beams is some array. And we'll only add the new beams to the list of beams that we should keep exploring if we haven't already seen it. So we're going to go through new beams.each, do beam, beams, shift beam if we haven't seen the beam before. Then at the end, we're going to say scene plus equals beams. And we want to add all of the beams that were valid, and we want to add our energized ones that are filtered out, because we need these scene ones to include the direction and the energized to keep us keep track of like where we've been so far. All right, this is looking great. This pattern matches what we're looking for. If you look at this, now we're off by 1, and in this example, we would have seen 46 energized tiles. We actually saw 45 energized tiles, and you'll notice that this top left one is not energized in our solution, but it is in the example. And part of that issue is that right now, our first beam is entering, assuming that we're starting on that tile. But we actually need to start off the grid pointing at that tile. So we can put this at -1. We can start our list of beams at -1. That way, when we run, we're properly energizing that cell there. Okay, that should work for the example input. Let's grab our input and grab our puzzle input here. Copy this giant thing, paste it in. I'm glad we don't have to manually go through and update all of those backslashes. Okay. And let's comment out this printing. We don't actually need to see it anymore. And then we'll leave in the one at the end. But okay, so now instead of example, we want this to come from input. Okay, run it again. All right, we've got some cool input happening here. And 6361 is our answer. And let's see if that matches. Yeah, 6361. That's the puzzle answer for part 1. Whew, awesome. Okay, let's take a look at part 2. Part 2, the difference is instead of just starting from that top left corner, we can start from any part of any of the edges, and we need to figure out what the maximum energized tiles are for any configuration. So rather than just going through the contraption once, we need to go through the contraption and get the best energy from the contraption. If we were to go through it from any angle, we want to maximize that energy. So let's take a look here. I think what I want to do is just refactor this whole thing into a new method called energy, and it's going to take in the beam and the grid, and it will do all of this work, and it will give us back the energy. So now if we just said something like P the energy of 0, -1 for the grid, and we run it, we should get back something. So now we need to create beams, start with this starting beam. Great. Okay. All right, 63, 61. Great. So now we've got something. So we need to go, okay, so this is for the 0 row. I want to go look at the first row and the second row and the third row and so on until we have explored all the different rows. So let's comment out the hours and look at the example. So we want to go through 0 up to grid size, and this will give us all the rows. And that's when we want to go right. And this will say, this is going to be X, and -1 means we're starting right off the left side of the grid. We're going to the right. And then we also want to start off of the right side of the grid. So this is going to be grid.first.length. And that should be because we're starting on the right side of the grid, we want to be going left. And we want to do this same thing, but for the columns. So grid.first.size, and then this will be Y. I don't know. Okay, so if we're starting at, this is actually going to be -1 Y. That means that we're looking from the top of the grid, and we're going to be going down. And then grid.size or grid.length or whatever. And this case, we're going to be going up and Y. I think that's right. I don't know. I'm pretty sure. All right. And then at the end, we're going to get some maximum energy, maximum power. All right. So what I think we might do is just say like max is equal to, 0. And then we'll say max is this, max.max. And same thing here, max is equal to this. And and say max equal to that max, and max here equal to that max. Now what is that? This is slow. So we're going to go and we'll see how fast it goes up and remove that statement. Oh, we still need to return that though. Okay. So what did we end up with here? That's actually wrong. Why is that wrong? Oh, this one doesn't have a max. Okay, there we go. So started at 46, we got up to 51, and that looks good. So the actual input is slower. So 63, 61. Okay, getting a little higher, getting a little higher. And there are 110 rows and 110 columns in the example input. And these are trucking through at 1 or 2 per second here in Ruby. So we can just let it run for a minute-ish. So that would be, that would give us like 110 times 2. Yeah, actually, we'll just do like times 4 because that should give us 440. We need to go through and solve 440 times. So if we just do some 440 divided by 60, let's assume that it takes a second per time to go through. We end up with 7 minutes, which is survivable, right? I feel like the part of computer science is just figuring out how long things are going to take and then figuring out what you can stomach. We are letting this run. And now that we see 6701 a bunch of times, this seems like it's probably the max. So we can come over here and look at 6701. All right, boom. That is the maximum for part 2. I had a couple ideas for how to optimize it. I think if you wanted to trim off some of the execution, you could cache and figure out, okay, as I'm solving this, if I encounter some tile where I know the cached maximum energy from that position out to the edge, then I can just return that instead of counting it up. But yeah, I felt like brute force was a little easier. Okay, so we did end and we got 6701. Let's take a look here and see if there's anything that we could improve. I don't think we need this case because it's covered by the bottom base case or the default case. And Yeah, so if we're going to the right or left, we want to go up and down. If we're going up and down, we want to go right or left. And then for these turn cases, I think we can combine these two cases and we can say if it's a turn at all, then we pass in front as our argument here. So if it's a slash or other direction slash, then we key into our turn thing and go the other way. There's probably a smarter way to do this beams situation too, but this seems to work okay for skipping over those scene ones at the very end. And then keeping track of what's energized versus what's not. We could probably do this with one single set. Like maybe there's a way to filter out which ones you've seen and exclude the direction. So potentially you could comment this out and then say scene dot length. And then we can remove the concept of energized here and use scene directly. So now if we run this against the example input so that it's fast. Okay, so now we get 51 in, that's pretty quick. And okay, so just for the sake of double checking, running it against the main input started at 2 minutes and 1 second. So let's run it again and see if it's any faster against the actual input now that we've made that change where we've removed one of the sets. And we only really need to do this step where we're mapping over and pulling out X and Y once per energy check, right? Like we're going to keep track of the scene. We need the scene anyways. We might as well just keep track of all of the scene and then, yeah, convert it back to a set and take a look. We're taking a chunk out of it, not half the memory, but we're taking a good chunk out of the memory usage by removing this other set here. So that should go a little bit faster. We're also removing like some set operations. Another question that I have is how else could we trim this down? So if you have thoughts or ideas, yeah, I'd love to hear. So this one, now it's 1 minute and 3 seconds. So we basically cut it in half the time by removing that one set. So that's pretty cool. Yeah, this is pretty neat. I'm really loving pattern matching. I'm using it a ton in this year's Advent of Code, really enjoying it. Hey, if you learned something new, I would really love if you hit subscribe. It's free. You just push subscribe. That's it. And yeah, it would mean a lot to me. Hey, thanks so much for watching. I really appreciate your time and attention. We'll see you in the next one.